Hi, I'm Whitney Espich, the CEO of the MIT Alumni Association, and I hope you enjoy this digital production created for alumni and friends like you.
Welcome to the MIT Faculty Forum Online. My name is Edith Won. I'm from the Department of Nuclear Science and Engineering, and I will be the moderator for today's event. This broadcast is sponsored in part by the MIT Federal Credit Union, MIT Professional Education, and MIT Sloan Executive Education. I'd like to give a special welcome to anyone from those units on MIT, as well as a special welcome to our colleagues from the Department of Nuclear Science and Engineering and the ANS. A reminder that after we hear from today's guest, we'll field your questions for him. Please use the Q&A feature on your Zoom toolbar to ask them, and we'll get to as many questions as we can. Today, we'll hear from Professor Mingda Li. He holds a PhD from MIT, earned in 2015, and he's the Norman C. Rasmussen Assistant Professor in the MIT Department of Nuclear Science and Engineering. We'll post a link to his full bio in the chat now. Professor Li's talk today is entitled A Tale of Two Singularities, Fundamental and Energy Applications on Topological Weyl Materials. Welcome, Professor Li.
Thank you, Edith, for the introduction. And hi, everyone. Welcome back to MIT, even virtually. So let me share my screen. So today we're going to talk about a type of topological materials called Weyl semimetal. So in the past decade, there have been really numerous researches on topological materials for applications like electronics without energy dissipation or for quantum computing, quantum information applications. But today, it's a specific type of the topological material called the Weyl semimetal, driven by a pair of two singularities. So the structure for today's presentation, I'll first give a crash course on the introduction on topology and their link to this type of materials, and give two examples from our recent research. One is more fundamental, how we can visualize the topology of electrons from the ionic degree of freedom. And the other, how we can use this singularity as a source to harvest energy. So first, the topology. So a very common or like even cliche examples is like the cup with a handle. It's just topologically equivalent to a donut because they both share this holes. But today I'd like to provide a few more examples in this area. So the first thing, topology is actually quite close related to geometry. So here is an impossible paper trick. So how can we make a paper cut like this? Just one single paper, no glue. And the other examples, when we try to hold a pizza, and we don't want to hold it like this, but we want to fold it along this edge, so it gains some rigidity and all the way to the tip. So to see why this is the case, so here actually the two sides, they are back and the front side of the paper, orientation matters. And in the right example, so it has a flat curvature. So when it's flat and even we twist it a little bit, it wants to maintain this flat curvature. That's gains to the rigidity all the way to the pizza tip. So the linking to the topology, that if we make it deform higher, that means it's also linked to continuous deformation. So imagine there is a very strong cowboy. So he may be strong enough to lasso a horse, put a lasso here and even multiple rounds, but may even have hard time to lasso a basketball. So all these lasso will just keep shrinking all the way down to a single point. So this is a very typical topological phenomenon. The lasso is a circle called S1, and put a lasso on the horse neck, which is another circle. We get this so-called first homotopy group. That's the number of invariant distinct ways to deform, and it gets different like integer types. And if we lasso this circle on the sphere, we get a trivial number of 0. So we might think, okay, this is really real life, not directly related to physics. But imagine if we generate this 1D example to 2-dimensional, then it directly gives the so-called integer quantum Hall effect. And this z as integer is just this number, integer number in quantum Hall effect. But today, So the type of the topology, as later you will see, which can directly link to the this Weyl semi-metal with sharing exactly the same mass, is by asking this question. So why almost everyone has this hair swirl or has a hair hole on the head? So that's a topological singularity. To truly fully understand this question, let's give some background introduction. So we have a continuous curve, and we can define a local curvature. So imagine if there's a circle that make it a tangent in this local area, and curvature is just 1 over this circle radius r. Imagine it's not a one-dimensional circle of curve, but have a two-dimensional surface. And we can generalize the curvature to the so-called Gaussian curvature for a cylinder, and we have these two principal directions A and B, and the Gaussian curvature is just the product between these two directions. And because we know that one direction is really flat, the Gaussian curvature is 0. That's also the reason why this pizza originally, before we just tweak it, it's 0 Gaussian curvature. After tweak it, it try to maintain the 0 Gaussian curvature and gains the rigidity along the radial direction. And here, what's related to the Weyl semi-metal is on the sphere. And everywhere the curvature is just 1 over r, so we get a Gaussian curvature 1 over r squared. And from there, we can define a quantity called the Euler characteristic. We have a closed sphere, and then just integrate the Gaussian curvature over the entire sphere and divide by a factor of 2 pi. And that Euler characteristic chi becomes an integer, and it has a physical meaning. That's the number of total singularities on that surface. And for this sphere, Gaussian curvature is just 1 over r squared everywhere. And we know spherical, the surface is 4 pi r squared divided by 2 pi. We get 2 singularities on the sphere. And that directly explains on the sphere, and if there's some vector field on top of it, and there are 2 singularities, and the head is almost like a hemisphere, and almost everyone has this 1 singularity. And if we consider our hair some vector field on this spherical surface. So very interestingly, so this type of topology shares exactly the same mass to the materials we want to introduce today. So that's the topological Weyl semi-metals. So here is the transition. So in the hair hole topology, so we are talking about a two-dimensional spherical surface that's in real space, R space. And we all know we can do a Fourier transform in momentum space. In Weyl semi-metal, that's also some sphere in momentum space. And just like we know there's some Gaussian curvature in the 2D spherical space, and in this 2D momentum space, by computing quantum mechanics wave function, we can also define something called a Berry curvature, and we call it F. And just like we have Euler characteristic on this 2D surface, here we also have an invariant like a Chang number, or we can call it a chirality here. It's just integrating over the surface, not in real space, but in momentum space. So consequentially, we obtain a pair of this Weyl singularities, we termed like a Weyl nodes. And they paired because they all have this opposite this chirality. You can consider like a light, we have some left polarized and right polarized light, and here for Weyl fermion, the left chirality and this right chirality. So that's this source of this Weyl fermion. The materials with this kind of singularity and the linear dispersive energy momentum relation that's defined a Weyl semi-metal. So to see how this Weyl semi-metal are why they are interesting. So here are a few fundamental examples. So one is chiral anomaly. So that's the breaking of the fundamental symmetry, which happened only in high energy physics, but now realized in condensed matter systems. And there are also some special circuit state, fully topological protected, and that can be used to build high performance electronics. And there are also some singularity to giant the thermoelectric energy. But the first question, we want to confirm that materials, it is a Weyl semi-metal as the very first step to further experimental studies. A typical step to confirm the materials is a Weyl semi-metal is a combined ab initio calculation and called this angular resolved photon emission this method, RPES. So from this density functional ab initio calculation, so people can obtain the band structure. You can see this linear dispersive, this Weyl cone, and here there's some singularity, and then carry out photon emission measurements. You can see this bands directly. But there are some limitations. So such as this type of the materials, they are very limited. They have to cleave it into like an atomically sharp surface in order to allow this kind of measurements. And we cannot in situ add some like a strain or magnetic field that will disturb all the signals. Or they also have a very high technical barrier, such as really need to maintain very ultra high vacuum. So the idea here, so can we really try to detect the topology of this Weyl fermion for this electronic degree of freedom by detecting the ionic degree of freedom? So the answer briefly is yes, if we can fully take advantage of these singularities. So to see how that works, and we know that the ionic degree of freedom, the basic quasi-particles, they are phonon, and the electronics, and when they link to phonon, they are linked by electron-phonon interaction. So electron-phonon interaction is really ubiquitous in many materials. So such as happening in determining like resistivity in metals, so carrier mobility in semiconductor, also can assist with some electronic transition or quantum information processing in diamond NV center, or even this conventional phonon mediated superconductors. And here, in the current context, but we know there's some limitation of all these examples. The conventional electron-phonon coupling, this strength is very weak. So if we use some dimensional constant, a dimensionless constant is almost less than 1/100, a very small amount of the interaction strength. But there is one actually exception called the Kohn anomaly. So the Walter Kohn is one of the pioneers also developed the density functional theory, but the Kohn anomaly works like this. So imagine we have a metal that's described by a Fermi surface and the one electron with momentum this K1, and after scattering with a phonon like wave vector Q scattered into another electron becomes the momentum K2. And Kohn anomaly happens at a very special condition. That means if the K1 and K2, they become parallel to each other, because these are like a periodic and these two points are nested with each other, that appears like there's no scattering at all. That leads to a sharp divergent change on the dielectrical function, and that will cause a softening of the phonon energy. And that's observed in some materials like lead in this particular example. But here we don't have a Fermi surface. It's no longer metal, but it's a Weyl semimetal with a few disjointed these topological singularities. So can we induce a Kohn anomaly in a Weyl semimetal? So in our very recent work, and we provided the answer saying yes. So here is how we did that work. So to show there is indeed a Kohn anomaly in the Weyl semimetal, so we first want to provide a theoretical prediction or the observation criteria, so where we want to expect the Kohn anomaly to happen. So after some quantum field theoretical polarization calculations, so we get a very simple criteria. So assuming if we have the two different Weyl cones, these two are two singularities located in momentum space kW1, kW2, and if the phonon with wave vector Q will link them together, and the phonon energy will also assist the transition, and it will generate the Kohn anomaly. And this phonon energy assistance is to this dynamical effect. So comparing to the conventional Kohn anomaly, here there are a few distinct features. So one is chirality selection. So because electron-phonon coupling, it preserves this chirality, and if there are two Weyl cones, only when they share the same chirality, like a right chiral to right chiral or left chiral to left chiral, then the transition becomes possible. If they have opposite chirality, then the transition becomes forbidden. And later we'll see we can experimentally test these predictions. So the second is that in some materials, like a conventional metal, the divergence is like a logarithmic. In some two-dimensional electron gas, like a graphene, there's also Kohn anomaly, but with some 1 over square root of the divergence. And in the Weyl semimetal, the derivation shows that there's a strong, really power law divergence. And consequentially, so the softening is not happening only at a single point, but also softening can happen at a nearby momentum space, like this bowl-shaped softening. Whenever Kohn anomaly happens, the phonon energy will just be dropped. And so with this kind of theoretical guidance, then we can start to prepare for the experiments. So for a particular type of the Weyl semimetal, so we choose tantalum phosphide, TAP. The reason is very simple. It's a very clean system that only hosts two types of these Weyl cones. We can call them W1 type and W2 type. Not only two, but they have like a 24 in total in the momentum space, but they're just located separately in the momentum space. And then in order to carry out these phonon measurements, we also need like a high quality, large single crystal. So we spent almost for an year of effort to try to find the recipe to grow really large centimeter size of crystal. That's like an order of magnitude larger than literature reports. And then we can provide this high quality experimental signatures. And for this particular of material, there's also one more interesting feature. We want to show that at the phonon wave vector Q, as the difference between two types of the Weyl node KW1, KW2, and that wave vector Q value, that will be Kohn anomaly. But that value happens to be another KW2 type of the Weyl node. So that gives a very specific kind of prediction condition. And we would expect Kohn anomaly happen at a Weyl node in KW2 itself, but not in KW1 type of the Weyl node. So among all these three-dimensional Brillouin zone or momentum space, we expect the Kohn anomaly to happen at a single and this very specific wave vector. But let's see how we see that. So this is this Kohn anomaly experiments. So if we have the two different singularities, W1 and W2, and assisted by the phonon with the specific wave vector Q and linking them together, that's how we observe the phonon softening. And see them in the original spectrum, or after plotting, we can also see that this significant 2-3 milli-eV, this phonon softening compared to this nearby magnitudes. And this theory predicts this criteria, and that criteria is met with very high precision, the less than 1% of the error. And comparing with the theory, which is the bowl shape, we don't have too many points, but we can see generally there is some softening, like a bowl-shaped parabolic this softening is also being observed. So contrary to that, if we go to another W1 type of the Weyl node, and which link the two different W2 types of the Weyl node, we won't be expecting Kohn anomaly. The reason is that this linking these two W2 Weyl nodes to meet this momentum energy conservation, they must have different this chirality, opposite chiralities. That's why we wouldn't see any softening profile there. So that's our main experimental findings, showing that this electronic topology singularity softening the phonon. So there are a few possible applications using this Kohn anomaly. The direct consequence is we can measure the electron-phonon interaction strength, because that is the parameter that determines like a decoherence of the quantum states, and also one reason why many quantum phenomena cannot be observed at room temperature. So that we hope that can be useful to indicate what kind of quantum material with some kind of weak electron-phonon interaction can possibly have higher temperature applications. So the other more technological relevant is on the so-called chiroelectronics. So just like spintronics, people use like electron spin up, spin down, degree of freedom. So that term came in the past 2 years. try to use the left chiral or right chiral types of the charge carriers in order to build electronics. And because in the current context, only the chirality conserved scattering is possible, there is some chirality dependent electrical transport there. But still, overall, this example is more fundamental. There are more practical use utilizing these singularities. So that's actually our main topic for today, and kept us very exciting in the past few months. So that's about using this singularity to really harvest the thermoelectric energy and breaking this upper limit by order of magnitude. So thermoelectrics is a way to convert like waste heat directly into this useful electricity. So the overall efficiency is directly linked to a dimensionless constant called Gt. It's proportional to temperature T and proportional to this so-called thermal power S. It just have a unit volt per degree. That means by varying the temperature difference for 1 degree, how much voltage we can gain. And it's proportional to S squared. And then it's proportional to the electrical conductivity, but inversely proportional to thermal conductivity. Intuitive understanding, if we have some materials with low thermal conductivity, that reduce the thermal loss and then can help to preserve the heat in order to facilitate the energy conversion. For the majority of the effort in the thermoelectric community is to separate sigma to K. So that's the so-called electron crystal phonon glass. The reason is that they have very different mean-free paths. So in many materials, the phonon can get strongly scattered in this like polygrains and grain boundaries, but electrons can penetrate through, and that can significantly reduce thermal conductivity K, but not to lose too much on the electrical conductivity. But less attention was paid on the overall factor called S squared sigma, and that's called the power factor, because there are some fundamental upper limit exists. So here's why. To see why there's some upper limit, let's first mention why metals, they are not good thermoelectrics. So metals have a very high electrical conductivity, as we all know. However, so metal has very low thermal power, because the thermal power intuitively is actually a measure of entropy with just a different unit. They want to convert some this heat into this electricity, then it has to be enough available states for the carriers to jump into. That means it has to have high entropy. But here, imagine this is the Fermi surface of the metal, and the metal only have this small range of really active carriers near the Fermi level EF. So the feedback, the thermal power is very, very small. So metal have very low CT, never almost good thermoelectric. So that's why the majority of the thermoelectrics, they are semiconductors. The sigma, the electrical conductivity is compromised, not too high, but it can gain the high this thermal power. So if we plot them together, so this is so-called Pitarenko plot as a function of this carrier density, higher and higher this electron this density, we know that the electrical conductivity will increase, but it has less entropy, and this thermal power will decrease. And if we put them together, multiply S squared sigma, there's some optimized peak value. And that is this fundamental limit, which makes it very hard to significantly increase power factor. And there's one more thing was mentioned, this S, if we have really random this particles, electrons, just like ideal gas, it's just like a KB over E. So which has this highly randomized this carrier to have a high thermal power. And so recently, this one physics professor, Liang Fu, in physics department, so he made a few predictions. So preserved some theoretical guidance, how we can use the topological singularity in the Weyl semimetal to break the barrier. So the first thing, so they showed that the high thermal power can be generated at a very high magnetic field. So for conventional material, if we apply an external magnetic field, there will be some saturation. But this Weyl semimetal, it will keep growing with the increased magnetic field. And the reason for that is largely related to a so-called quantized thermoelectric Hall effect. So we know quantum Hall effect, the Hall electrical conductance is a universal constant. So in this example, so this alpha xy is called thermoelectric Hall conductivity. That's the transverse thermal current over longitudinal electrical current over temperature. That will reach to a universal constant. And this is the number of the Weyl cone, that's the Fermi velocity. And then all the rest are universal constant. And so he showed that if we want to make this happen, the transverse thermoelectric Hall and the transverse resistance will have to dominate the longitudinal thermal power. So that is very contrary to conventional material. Longitudinal thermal power is dominated by longitudinal thermoelectric response. And another thing, so when we apply magnetic field, there become a problem called localization. So that's just from the Lorentz force. This charge carriers will experience a force this perpendicular to the moving direction. That's why the electrons will tend to have this circular motions. And then this electrical resistivity will be increased significantly. But for the Weyl semimetal, as we know, there are two hair holes in the momentum space and very robust and cannot break. And this make it remain metallic state and reduce the longitudinal resistivity. So that's a little bit twisted, but here is a summary. We have a quantized value of thermoelectric conductivity. When it's dominant, there can be a high thermal power, which means high voltage gain per temperature gradient. And if we can still make it maintain low longitudinal resistivity, we can get the high power factor S squared sigma. So that's three things separately, but with increasingly stringent realizing condition. So here is our recent experimental work showing these predictions. So the first, this transverse thermoelectric Hall conductivity. So that's actually a combination of four independent parameters, like SXX, rho YX, SYX, and rho XX. So longitudinal, transverse, electrical resistivity, and thermal power. And the first thing we show that it reaches this unified universal constant when we apply high magnetic field and agree quantitatively with the theoretical predictions. Because as we imagine, all these parameters like longitudinal resistivity is certainly highly dependent on temperature, on magnetic field, and even material specifics. And here, after the combination of four independent parameters, the final number becomes independent of anything on the material specifics, only highlights the contribution from the topological singularity, making it a universal constant. And the second thing is more related to this longitudinal thermal power. As we can see, so this line is some ideal gas entropy can be reached. And if we have this very low transverse electrical resistivity, and we can show there is a really increase this value of this longitudinal thermal power, reached a very high this value, and also at a low temperature. So the difficulty for low temperature can be understood because many thermoelectrics are working at a high temperature, far above room temperature, because that's good to increase the entropy. But here the peak value is about like 50 Kelvin. So the in general materials, the entropy are very low, but still can reach very high this thermal power, like an order of magnitude higher than the ideal gas limit. And to see that this is indeed the case dominated by this quantized thermoelectric Hall, so just can decompose this longitudinal thermal power into the two contributions, and we can see this transverse part of the thermoelectric Hall can dominate this whole 90% of the longitudinal thermal power. So the last thing we like to show is more related to this power factor. So the power factor is this like S squared sigma or S squared rho to be more precise using a tensor language to give a comparison. So this top row is an example on the another topologically trivial semimetal like a bismuth. And it has like a power factor about 5. And for this Weyl semi-metal, it's about like 500. So that's also like 10 times higher than the best like thermoelectrics, like lead telluride, bismuth telluride. But those materials, they reach very high this power factor at elevated temperatures. And it's also 100 times higher than the similar type of the semi-metal materials. So at this stage, and we can think that we can truly utilize these topological singularities as a source to harvest energy. As a brief summary, so today we provided two examples on using topological singularities, and first to induce this Kohn anomaly, which is we can see electronic topology using the lattice degree of freedom with a few novel features like the chirality selection between the singularities and a phonon energy assisted dynamical effect and also a power law divergence. So this one limited by the instrument, we cannot confirm or deny at this stage. And then the other more practical energy application is we can use that to generate a giant thermoelectric response. The one thing is related to the more quantized thermoelectric Hall conductivity. Even the materials resistivity, thermal power, they are all highly dependent on materials, temperature, magnetic field, and the combination is really a very simple this universal number here. And there is also large linear proportional to magnetic field, non-saturating thermal power here. And finally, and just using the singularity, we can also generate high thermal powers with order of magnitude higher than reported materials. So with that, I will just stop here and acknowledge my group members and all the collaborators and the Department of Energy for the support. So with that, thank you for your attention. Happy to take any questions.
Well, thank you, Professor Li. I'd like to just take a few minutes to remind alumni and anybody else who is watching today that you can ask questions by using the Q&A feature in Zoom. And you can also upvote questions that have already been posed. So let's give people just a few seconds to type their questions in and upvote anything that they're particularly interested in hearing about. All right, so I'm seeing some upvotes for a question about any sustainability implications of this work. Professor Li, is that something you're able to address?
Yes. So many questions. There are some earlier questions. Shall we start from there or back to
I was going by the number of votes that a question had received, but we'll start with the one from the very beginning, then we'll jump to the most popular one and sort of go back and forth. Okay, the first question was about a project developed by Bill Gates that was addressed in his Netflix documentary regarding small nuclear plants being used in radioactive fuel. Is this something that you think is feasible? And is there any reason why the US shouldn't be promoting this? I don't know if you're able to draw any connections between that question and your talk.
Yes, I think that's actually a great question. And there are also the deep connection between the like NIC and their alumni and working with like very small reactors and even this next generation reactors. I'm not certainly expert in working with this reactor, but there are certainly many feasible components there to promote it. And I believe that's also maybe Bill Gates may have some confidence that may work out and with very good permitting results. And for this US, why not promote that? I think that's there are many practical issues here, like the regulation and other things. But when the time is good, I'm pretty sure there are still many exciting opportunities in the next generation reactors. I still feel optimistic in that area.
Oh. Well, thank you for that answer. I'd like to go back to the question, which was still the most popular one. I think people are interested in hearing about the sustainability implications of your work.
Yes, so thermoelectrics has been really brought up almost like 50 years, and comparing to other this energy harvest method like the solar panels, it has been less implemented. One major reason is the CT or this efficiency is not high enough. And here, what we will say, if we can really find a highly distinct mechanism that can break the barrier and truly make use of thermoelectrics as a source of the energy, it can actually harvest many like a waste heat, not necessarily using like a sun, and it can be used like even some waste heat in our home heating system or even our body heat. So many of these kind of waste heat, they compose of like 60, 70, or even higher percent as rejected heat in our current US energy structure. And imagine if we can use those amount of the waste heat to do energy conversion. So that will be the main driving force to support sustainability. Hope that answers the question.
Right. If people have follow-on questions, please feel free to type them up into the Q&A feature, and we can continue with particular threads if there's a lot of interest. Next question. These questions are very broad in range, which makes this fun. Some people are wondering, it says, some folks have two whorls on their hair. How do you explain two local topological singularities?
Yes, that's a great question. Let me show you from the explanation in that page. So some people can even have three, but more likely there are two will cancel out as one positive chirality and one negative chirality. And here you can see I use the term approximately. The reason is that the human hair is not a full closed sphere, but more or less a hemisphere. So that means we can really actually push another singularity into the sphere, but with the overall energy like a higher. So that's the case. So it not becomes so mathematically rigorous. It's not a really like ideal sphere in that case.
Thank you, Mingda. Another question, jumping topics again, how difficult or expensive is it to manufacture these Weyl semimetals at volume?
That's a wonderful question. So at our lab scale, I would say this is for the fundamental measurements, the cost is not a concern. So I think we are still at, haven't reached that stage. We still want to get a higher quality crystal and make it measurable and like a high precision thermal measurements. We really needed to have a high quality, large single crystal to even carry out this type of measurements. The brief answer, this cost is high. And but we would think if there's some highly promising materials, then gradually it will come to the stage for the mass production. There's still a few different hurdles to overcome in order to achieve that. So right now it's far from that scale.
Okay. Can you talk about the range of temperatures over which these materials are likely to be useful?
Yes, so that's a great question. For these particular materials, and if it's below like a nitrogen temperature, so you can imagine if we want to do something at a cryogenic temperature, we use liquid helium at 4 Kelvin, liquid nitrogen 77 Kelvin. But thermoelectrics, if we run it backward, which means that we inject the current and can make it cooling, as the Peltier effect, and we can actually do cryogenics without using nitrogen or helium. So if we have some material with high performance near helium temperature, we can make a refrigerator. And currently people are using like a helium-3, helium-4, like that kind of dilution to a fridge. And then we can use some like a cryogenic-free fridge by using thermoelectrics. So that is one major application. But the other major application is certainly to push it into room temperature range. And that's as long as the materials, let's say the materials, by material we mean it has a brilliant zone, a momentum space, and all these singularities, they are fixed, then the working temperature is almost fixed. So imagine if one day some people design a real very optimized material just for room temperature, that can also be permitting and to make the working range tunable, but not at this stage.
Mm-hmm. We've got another question. Why would one prefer energy harvest from thermoelectrics over methods like heating steam and running a turbine?
That's a great question. So heating, actually the reason is just the answer. So the heating steam or the turbine, they have moving parts. So one reason people promote thermoelectrics is that it only needs a fixed static part of semiconductors without you having any moving parts. And the other is also the heating steam, the turbine, they really are harvesting from high quality heat. And we don't want to do turbine in our body, and even some like international, the Internet of Things, and this tiny amount of the waste heat generated from our daily equipment, from our body temperature. Those kind of heat can also be harvested using this small device of the thermoelectrics. That's another application area, not possible for the turbines.
Mm-hmm. We've got a question now about the people doing this work. Can you talk about your grad students and how they're doing? And people are also curious who your biggest competition is for grad student talent.
Yes. Well, I think overall, these works are done and led by graduate students, and we don't have many. If we're talking about my own research group, we have 4 graduate students. One is not listed here. I think they are doing great, and I feel very lucky having them working together with me on all these topics.
Mm-hmm. Can you comment a bit on who your biggest competitors are, or is that a trade secret?
Competitors, I would say there are few groups we have the shared goal and try to achieve the same thing. Sometimes they reach some competition, but overall, I feel it's all like also a constructive competition. Some other groups, they tested new phenomena in different materials, like this quantized thermoelectric Hall. Another group, they tested in Dirac semimetal, and we do Weyl semimetal. So that's sort of a competition, but I feel we both contributed constructively to confirm some novel mechanism going on in these types of like singularities. So not so worried about the competition.
Okay, thank you. We have a comment from David Quinn. David, are you still online here? If you are and you wanted to make your comment live, please feel free to do so. David had a comment about waste heat application and how it would probably work very well for combined cycle gas turbines. Mingda, I don't know if you want to comment on that.
I think that's certainly very true. And this waste heat in gas turbine, it's working already very kind of mature and going on extremely well. And so that's, I really don't think that's the field for thermoelectrics working at that kind of environment. I'm still thinking at a different application scope, like in my office, we have the heating system, very small things, or even like this, we have a computer that kind of very low grade waste heat. So that's a kind of waste heat is which much lower quality than the waste heat in gas turbine, and also much lower this temperature gap, but still there's some chance to generate electricity from there. So, but I would say yes, there's a very permitting this going on in gas turbine itself.
Thank you. David, if you had any other comments, please chime in. I'll go on to the next question. What predictions do you have for quantum computers being 100% fault tolerant and being mass produced?
Yes, that's an awesome question. I think it's just like classical computers, there's also this error and fault on quantum computing. There are two things at least going on top. One is topological quantum computing, so that use like some non-local states, and so destroy one won't destroy the other. That's provide some like a layer of topological protection to make it like a fault tolerant. But the other thing is just like a classical computer, there's also some post-processing, like the error correcting codes and algorithms. And I'm sure there's active research in in the quantum computing. They are also designed this kind of fault tolerant algorithms. And so it doesn't have to be 100% error tolerant just by the materials itself. They can even correct afterwards.
Last question here. If anybody else has any other questions, I'd encourage you to type them into the Q&A function. Are there applications for heat pumps, heating and cooling in conjunction with electrical production?
And so I'm not entirely following the question. You're talking about thermal. It sounds like more or less like a thermoelectrics. There is a heat source, there is a heat sink, there is a temperature difference between that two parts, and we can produce electricity from there. So that's the essence for thermoelectrics. So that might be the answer to this. But maybe the audience have the specific configurations in this stage.
Well, thank you, Professor Li. That was a very informative talk, and you certainly answered a range of questions. I'd like to thank you for your time, and on behalf of the Alumni Association, thank you everyone for tuning in to the MIT Faculty Forum online today. We'll be keeping the Q&A up for another 15 minutes or so if anybody wants to, actually, sorry. An additional question just popped up. Going back to the question around temperature range, is there any chance we could find thermoelectrics that work at or below the He4 boiling point?
Actually, brief answer is yes. There are some other materials people have been studied, some kind of weird iron-based compounds, and they actually work at a very low temperature and with a very different working mechanism with like a Weyl semimetal, but it certainly is possible.
Okay. Well, thank you for addressing that last question. As I was saying, we'll keep the chat window open for another 15 minutes or so if anyone wants to network. This broadcast will be available on the MIT Alumni Association YouTube channel within a week of today's airing. Once again, thank you for watching, and we hope to see you again on a future broadcast.
Yeah, thank you, everyone. Thank you. Bye-bye.
Thanks for joining us. And for more information on how to connect with the MIT Alumni Association, please visit our website.